are gonna go over the assignment 1, and also we are gonna actually take some time to get into chapter 3 for a little bit. But we are gonna go through like assignment 1 first. Try to actually do some explanation on the coding part. So this part is gonna take about 30 to 40 minutes, and the last 1 hour is gonna be on the lecture delivery. Okay. So this is the first assignment. Basically, this is the simplest assignment of all the 5 assignments you're gonna have in the future. So this assignment mainly focuses on the word vector creation or word embedding creation, as well as the dimensionality reduction, which is gonna use like PCA or truncated SVD here, which I'll show you later. Okay, so let's go through by question here. So part one is content-based word vector. So basically, this part is actually asking you to construct, try to construct a word occurrence matrix like this. So you have a start, which means, oh, this is the start of this kind of sentence or that file. And you have the end, which tells you this is the ending of this sentence right here. And all the letters or the words in between is going to be the words we're going to capture in the word embedding. Okay, so basically, if you have 2 documents here, all that glitters now go, all is well that ends well. So if you look at this matrix here, start doesn't follow start, so it's going to be 0 here, and all start follows all twice, or all follows start twice, right? So start is some like this thing that's actually between before the all here, so it doesn't show up in the sentence, but we're gonna make it ourselves. This is called padding. Okay, I'm gonna type here. This is called padding. The chat box. Padding is very commonly used like techniques, especially when we have multiple variant kind of sequences over there. For example, if you try to put like a bunch of sequences into the neural network, some of the sentences, we try to classify the sentence, right? Some of the sentences may have 10 words, some of the sentences may have 20 words, right? So how do we actually make sure they all have the same length? Because we need to actually use the same length for all the words over there, because we need to construct, matrix like this. So we need to pad them. We need to pad the short sentence that doesn't actually have the words in the longest sentence with 0, or with some kind of like, I would say like, kind of like really trivial, that some kind of like, kind of techniques or some kind of like a starting and ending marks here. So this is called padding. Okay, we'll talk about this later with more details over there. Okay, so this part. All right, so as you can see here, this is the word occurrence matrix. All the words are here, and basically you are counting the occurrence of the words followed by the previous word or around the previous word. For example, start followed all twice, and all is around start twice. So it's 2 here. Basically, it's the same all the time. And that all follows by that, or that is actually around all here, right? So it happens once, so it's 1 here. Okay, 1 here, and it's 1 here as well. Okay, so we already actually went through that part, so I'm not gonna actually tell a detailed story about that part. So let's skip to the question here. So first part, okay, all right. So this is another kind of like a really general introduction in the SVD here. So if you actually miss the first 2 lecture, like how do we actually reduce dimension of this word occurrence matrix into smaller matrix, make sure you go through this part. Okay, so basically we're doing singular value decomposition SVD here, or you can do PCA. Okay, so PCA has many different kind of like a dimensionality reduction techniques, and SVD is a part of the PCA. Like PCA has some kind of parameter or arguments that can actually make sure you use SVD or other kind of like SVD. over there. Okay, so now I'm not gonna go through this part, so let's skip that. So first part here, plot a co-occurrence word embedding. So the ultimate task or ultimate goal of this question is that we are gonna plot, our word embeddings, our words on the 2-dimension kind of like coordinates or hyperplane over there. Okay, so the first part is not a question. Basically, you have to load the corpus here. So basically, we just actually imported this right here. So if we go back in here, okay, we have a bunch of libraries here, and this is like the corpus we're gonna load previously. Okay, basically it's a long online corpus like we're gonna use here from an LTK library here. Okay, and we also need like a NumPy here. We're gonna use this many times because we're gonna do a lot of matrix manipulation. So NumPy is definitely one of the packages we need. We're gonna use some random we're going to generate some kind of random seeds or some random parameters. So we need this as well. SkyPy here, we're going to use that one as well, which is also for the matrix manipulation and calculation. And most importantly, we also need the SVD here. So we are not going to do our craft the SVD ourselves. We are going to actually use the sklearn decomposition truncated SVD. They already actually have that kind of library, so we're gonna not waste of time actually using start over to creating our own SVD here. And the second dimension reality reduction is a PCE here, also from the same library. Okay, that's pretty much everything. And also, here we also need this matplot library because we need to plot, the simple like 2-dimensionality word embeddings. Okay, all right, so first part. First, we actually find the category. We just load the category. So this kind of corpus has many different subcategories, of corpus. We just need a category, this subcorpus. So this is gonna be our entire corpus. Okay, so it's category. So what do we do here is, first of all, I'm gonna transform all the words into lower letters, not capital letters. And second, for all the files, so this corpus has multiple files, okay, and all the words are inside one file or another, okay. So basically, for each kind of file, what I do here is I'm gonna list all the words, but also I'm gonna pad the word with a start and end token for a file. So after you finish that, if you print like the first kind of 3 file here, as you can see here, it's going to be like this. Start means this is the start of a file. Sorry, excuse me. And then a bunch of like words inside this kind of file, and you're going to have an and padding, which tells you this is the end of file. Okay, so this is one file, second file, third file, fourth file. Okay, so that's basically, this is actually the corpus. This is actually the corpus, the entire kind of like a dictionary we're going to use for the next kind of task here. So first question, implement the distinct words. So basically the first kind of like, function asks you what is the number of distinct words, right? And how does that look like in the corpus? So basically we have to, so that's really the question, write a methodology to work out the distinct words that occur in the corpus. You can do this with the for loops, but it's more efficient to do with the Python list comprehensions. So list comprehensions works way much better than use a for loop here. In particular, this may be used for to flatten a list of lists. If you were not familiar with Python list comprehensions in general, just click this. Okay. And also another kind of important hint is like you're going to use a Python stats to remove duplicate words. I guess this is like basic knowledge you should have for Python's data structure. Like sets only contain non-duplicated words, okay? And list can contain like same words or kind of repeated words, but stats doesn't accommodate same words, okay? So that's why we are going to use the stats here. So basically first, we're going to make a container or some kind of corpus where distinct corpus where list here. and then it initiates a number of the corpus words, distinct corpus words as -1. You can initiate as anything like a non-value 0 or any number, but I'm just happy to give it a value -1 here. So next, what I'm going to do is first for all the files and all the words in each files. Okay, what I'm going to do is I'm going to take a set so that I can actually only extract the distinct words. And next, I'm going to make the set into a list again. I'm going to sort all the words in alphabetic order. Okay. So this is actually going to give us this distinct like a word corpus, not the previous one. This one has a lot of duplicates, but this one here has distinct words. So the next part is we're going to actually try to calculate the length. So we return the distinct corpus words and the length here. Okay. Any question with this part? Any question with this part? All good? If you don't have any question, I'm going to move on to the next question here. If you have any question, open your mic, just speak out. Okay. Question 2. This is a bit complicated. This is the compute to occurrence matrix function here. So what this question asks is, write a methodology that construct a occurrence matrix for a certain window size n with a default of 4 here, considering words n before and n after the word. So basically, you have to construct a word a window size of 4, and you have to consider like a word 4 before and 4 after the word. Basically means that window size is 4, okay, in the center word of the window. So we are going to use NumPy here to represent a vectored matrix and also tensors. Tensor and matrix, they are pretty much the same. So you can think about it this way, like a vector. Vector is like, excuse me. So vector basically is like, one row or one column. You can think about that way. Matrix means you have multiple row, multiple column, but this means you are going to have a multiple matrix over there. So basically, matrix is made of vector, tensors is made of matrix. You can think about that way. Okay. So if you are not familiar with the NumPy, then here's a tutorial. Just go through that. Make sure you understand that part. So we are going to construct a co-occurrence matrix here. So what are we going to use? First, the corpus. Second, the window size. Okay, so that's the 2 arguments we have to actually use for the function here. So first, what I'm going to do here is, I'm going to generate the distinct word corpus. I'm going to use the function I had previously here, which is going to give me the distinct words and the word like the corpus length, how large the corpus is going to be and what the corpus looks like. Second, I'm going to initiate the matrix with none, or you can initiate the matrix with like if you already know like a dimension, you can do it that way. But because I don't know a dimension yet, so I'm going to actually initiate none here. So next part is I'm going to initiate like a dictionary with the words as a key and index of the words in the corpus as the value. Okay, so that's the dictionary here. Okay, so that's another kind of like data structure of Python dictionary here. Okay, now since I know that M is none, but I'm going to actually feed this kind of matrix with a bunch of different values. How do I do that? We have to know the number of columns and number of rows over there. So we have to construct the matrix with a bunch of zeros. So we can do that by using the length of the corpus, right? So I'm going to construct the zeros, a bunch of zeros in the matrix. The matrix dimension is number of times the number of words, which is n by n matrix, which is a square matrix here. Okay. All right. Okay. Next is I'm going to construct the word index dictionary. So basically, what I do here is for each kind of words in the distinct corpus, word corpus here, I'm going to generate 2 things in using enumerate function. Basically, the first word, I'm going to generate one first word. the second word is going to be 2, second word, so on and so forth. So it's going to be like two kind of like a list. The first list is the index. The second list is actually the word itself. Okay. So what I do here is for each kind of word, I'm gonna give the index, which is the order of the word in the corpus. Remember previously we actually sorted the words. So basically the index here represents alphabetical order of the word here. Okay, let's just pause here for a second. Any question here? You guys all know the dictionary, and you guys all make sure you understand this part, okay? Because we're going to use that many, many times later. Okay, no question. Let's move on here. Okay, next, for each file in the corpus and for each kind of like, so we're going to actually break the corpus into files, different kind of documents or files here. Second, we're gonna, break the document into a words, but we actually do that in a different way. So I actually do that in a different way. What I do here is basically I use the index to represent words here, okay? Because I just created, this kind of word index. So basically for each kind of document here, I'm actually gonna generate a bunch of index for each word over there, okay? So for example, if you have, so this index is different than that index, okay? So make sure you distinguish between the two. So basically that means, for example, I know who or you guys are silent. Okay, so suppose that's the first file 1. So what I'm gonna do here is, this is 0, index, next word, index 1, 2, 3, okay? So basically that's what I do. Use like an index within each kind of file to represent the words here. So next, I'm gonna generate a center word, because I have to generate, since for this kind of word matrix, I have to generate a center word and also have to generate a context word. So let's generate a center word first. So what's a center word? Center word basically means every single word, because you're gonna make every single word here, like you as a center word or guys as a center word. We're gonna loop through every single word over there. Okay. So what we do here is, first of all, for the word index within document, this gives us the exact word itself. Okay. So this is gonna give us the word itself. For example, if here is 2 and it's document 1, that's gonna give us this word here. And with that word, I go back to the dictionary, I can find the words index in the corpus. Okay, so basically I use a word index in the document to find the words index in the corpus. Okay, so that's how I actually fix the position with the center word. Okay, so that's how I find the position with the center word. So this is gonna give us the position with the center word. So next, what I do here is actually I'm going to generate a context word. Okay, so since the context word is like, it's going to be 2 window size before and window size after. So I generate a context word within the window size, so 2 times the window size. Okay, for example, if the window size is 2, that means, for example, here's the center word. So previously we're going to have those 2 words, and we're going to have another 2 words after that. So in, totally or generally speaking, the length is going to be 2 times the window size. Okay. So first, let's think about some exception here. If I equal the window size, or that means you're basically as a boundary of the window size here, or word index minus window size plus I smaller than 0. So this basically means we're out of the left boundary. We are out of the left boundary, because I represents every single word in the window size. If I plus a window size, actually is gonna be greater than the word index. That means basically you are jumping out of this kind of window size. Okay, so or you can jump out the window size from the right hand side. So word index minus window size plus I is greater than the length of the doc. That means you are not in this kind of window size anymore. So if that's the case, let's continue. Let's just skip that part, skip whatever is gonna happen here. So if it's not, if actually inside of window size, what are we gonna do here is we are gonna actually, find the context word. So this is the index of the context word in the document, similarly to this one here. So we find a word in the document and we return that word's index in the corpus so that we can find the position of the context words in the corpus. Okay, so we find the center word, we find the context word. The next is, because we are gonna, like put all the numbers into the matrix. Because in the matrix, we have the rows, we have the columns here. So basically what we do here is, center word, context word, right? That is, you're gonna do this dimension here, like, do that first, do this second, right? Because you have two dimensions, rows or columns here. So basically what you do here is I'm gonna, put the context word as my rows, and I'm gonna put the center word and my rows, context word and my columns. Then I'm gonna put all the numbers over there. Okay. Secondly, you also have to do like another order in the reverse order. I'm gonna put my context word treat my context word as the rows and treat my center word as the columns, right? Then I'm gonna actually, put all the currents over there. Why is plus equal to 1 here? Why do we actually use the plus equal to 1 here? Anyone? So the question is, why plus equal 1 here? Why is not 2? Why not 3? Why is 1 here? Yes, basically we are actually counting the currents of the word. So we actually, every time we have a new word, we're gonna actually count it once, right? So we are gonna actually, add a 1 on top of 0. Okay, so basically this is gonna give us, the word occurrence matrix over there. And a question about this part. Any question about this part? No? Okay, so what do we return? The word occurrence matrix. And what do we return? The index of the word in the corpus. Okay, we're gonna return those two. So this is just a test case. As you can see, I passed all the tests right here. Okay. So that's that question. Question 1.3 here. Reduce the k dimension. This is where we use the SVD here. Okay, this is really, really simple, I would say. Okay, so basically construct a method that gonna perform dimensionality reduction on the matrix to produce k-dimensional embeddings. Use SVD to take the top k component and produce a new matrix of k-dimensional embeddings. So how do we do that? So basically we have to truncate, the dimension this way. Basically, after I do the SVD here, I specify like I just want this type of the word. So basically what you do here is you're gonna truncate, suppose I just want the first 3 words, you're gonna truncate here and abandoning all the words after that. Okay, so you're gonna do a rectangle kind of truncate or SVD over there. So what do we do? It's really simple. First of all, you have to use a matrix because you are doing the the SVD on the matrix word occurrence matrix. Second is how many words you want to keep over there. How many core like important words you want to keep it over there. Okay, so it was default as 2. So next, it has some kind of arguments already wrote here for you. First is iteration. It's going to be 10. Okay. So you have to use this parameter in the truncated SVD function we're going to use later. Okay, so M reduce again is going to be none because this is a reduced kind of like a word occurrence matrix. So I don't know what it's going to look like yet. Okay, so I just give the value 9 here. Okay, so next I'm going to call the truncated SVD function here. So truncated SVD, the components tells, this is the arguments where you can pass to the function, tells the function like how many words I want to keep, which is k here too. And iterations equals the number of iterations. Okay, so after I call the function, I just phase transform the matrix. This is gonna be the reduced matrix over there. Okay, so that's why we actually give the null value at first. You can give the n value, to be honest. Then you can replace it with this function here, and you're gonna return the m reducer function over there. Okay, so this is like after the SVD, the reduced like matrix over there. Again, I pass all the tests here. I think that's super easy. I don't have to spend some time on explaining that part. Okay, so next part, plot. Okay, so here you will write a function to plot the set of 2D vectors in 2D space. For a graph, we'll use the matplotlib library. Okay, so again, the keywords is 2D vector, 2D space. Okay, how do we actually decide what's a 2D vector? Basically, the 2D vector is gonna be the row and a column in the matrix. Okay, we're gonna use the row as the X, we're gonna use the column as the Y. So we're gonna plot in that way. For every single row and every single column, we can find a specific number over there. Then we're gonna plot, the position of that number. Okay, so it's again super easy. So what do we do here is, first of all, I just because I wanna to show the figure a little bit bigger, so I just fix the figure size to 10:6. It doesn't matter. But next, here's the key part. For each word in the okay, so sorry, first I forgot about this part. So first, it has 3 arguments here. First one is reduced word matrix, which is a word matrix after SVD. Second is a word index of the distinct word in the corpus. Last is the distinct words, like the entire corpus. So for each word in this for each word in the corpus here, what I'm gonna do here is I'm actually gonna generate the reduced a matrix. I'm gonna, what I do here, first of all, this means a row, right? I'm gonna use a row as the X. So next is I'm gonna find a word in the word index, like a dictionary over there, finds the index of that word. And for that, because once I find the index of that word, I can use that index to find a specific word in the reduced a matrix, right? Because the way I construct the matrix is I use the index from the word to index dictionary to construct it. So if I just want to retrieve a specific word, I can use this word to index dictionary again, just like what we did here. So if you go back here, see, that's how we actually construct, not this one here. That's actually how we construct the word, because we use word to index dictionary here. Okay, so this is going to give you the X, this is going to give you the Y, which is a row and a column index of the word. Okay, so after that, what are we going to do is we're going to just plot X and Y, and also I just put some kind of text here so that you can see, the specific word over there. So after I plot that, as you can see, it's exactly the same as the answer. Okay, so this is the X, that's the Y, this is the row, that's the column. Okay, any question here? All good. People who actually did the assignment, I think Le Yuan and Yusa. Do you guys have any question here? Or you guys okay? You can talk, it's okay, you can talk. You don't have to, yeah, okay, all good, perfect. Okay, to make sure we are on the same page. So next part is, so this is another question called concurrence plot analysis. So now we'll put together all the parts you have written. We'll compute the concurrence matrix with a fixed window 4. So basically we're gonna, use a new kind of corpus. Actually, we're gonna redo what we did previously, but compressing every single function into a big task over here. Over the crude oil corpus, then we'll use SVD, truncated SVD to compute 2-dimensional embeddings of each word. truncated SVD returns U times S. And so we need to normalize the return vector so that all the vector will appear around the unit circle. So this is basically what you have to do for almost 99% of the truncated SVD or dimensionality reduction. Always remember normalize the reduced matrix over there, because sometimes, you know, as this one here, see, it's because we just, you know, it actually just plot these values here so that you can actually see it's from -1 to 1. But for this kind of matrix, it could be like the range or the scale of the x and y could be very different. So you need to normalize those kind of return vectors here. Okay. So let's see what we can do. Okay, so the line of the code below this normalizing using the NumPy concept of broadcasting. Does anyone know what broadcasting is? Or anyone doesn't know what broadcasting is? You guys all know what broadcasting is? No? Okay. So what is broadcasting? Generally speaking, is dimensionality extension. Dimensionality extension. For example, suppose I only have one dimensionality kind of array here. So that's a one dimension array. Okay, 2018. Okay. So what if I just want to extend? What if I just want to broadcast this kind of like an array into 4 dimension, 5 dimension, 6 dimension? Because sometimes I need to match the dimension with the previous like a matrix so that I can make the, you know, kind of like, for example, I can make this kind of like, you know, matrix multiplication. So let me give you an example. Suppose we have matrix A, we have a matrix B. A matrix A is a matrix of 2 times 3, okay, 2 times 3 matrix. A matrix B is just a matrix of, I don't know, let's see, 2 times 1, 2 times 1. And I just want to multiply A by B. And what are we going to get here? 2 times 3 times 2 times 1. Nothing, right? So I can now do matrix multiplication right here. So how can I, what kind of methodology or what kind of solution is a way out of this kind of problem? Suppose I really want to get a multiplication of A and B. What should I do? So you can broadcast the B here, right? You can broadcast the B so that it has a dimensionality of 2 by 3 again. Okay, so after broadcasting can be, you know, you just extend the dimension. So previously B could look like, you know, 2 rows, 0, 1, 1. Oh, no. 0, 1, right? It could look like this. 2 by, of course, in Python, it look like this. Okay. So mathematically speaking, we don't have the inside, like, you know, brackets, but in Python, it looks like this. Okay, 2 times 1 here. Okay, but what if I just want to multiply A and B? I have to do the broadcasting on B. So what I do here is, what I'm going to do is I'm going to broadcast this in this way: 0, 1, 0. Ah, damn it. Oh, no. I'm going to copy and paste here. See what we... Okay, so basically what I do here is after broadcasting, I just add some kind of value, like 0 here, to make it like a 2 by 3 matrix. Okay, basically I extended like the dimension right here. I extended dimension here. So in that way, you can do this A times B, A times B transpose. Okay, 2 times 3, 3 times 2, and you get a 2 by 2 matrix over there. Okay, so this is the simple idea, the general idea of the broadcasting. Basically, you have to extend the dimensionality, increase the dimensionality of a specific small matrix so that you can actually put it into or a bunch of like a calculation with the other matrix over there. Okay. 2 rows, 1 column, yes. Sorry, I think I made a mistake, right? Sorry, I think I made a mistake here. Yeah, I think it's 2 rows, 1 column. Yes, yes, sorry. So B should be, I guess it should be 0 and 0 here, and it's going to be this. Yeah. So again, the idea is actually the same. You're going to put this into yeah, or you can say B is 2 by 2. So my kind of like a core idea here is like it doesn't match like a previous like matrix, right? So you have to think about a way to broadcast it to make it like in the dimensionality match the previous matrix. So it's 2 by 1 or 2 by 2, it doesn't matter. What I mean is like you can actually extend the dimensionality using the broadcasting. Okay. Does that sounds okay? Does that sound like rigid to you guys? Okay, yeah. So what do we do? How do we do the broadcasting here? There are many different ways you can do the broadcasting, but here, Chris Manning, Dr. Chris actually just give us like a really simple way to do that. I'm going to introduce this maybe later. Let's look at what we're going to do first. So since we are going to start over from like with a new kind of corpus. So first of all, we're going to read the corpus here, which is crude oil corpus. Second, what I do here is actually I'm going to construct the occurrence matrix, right? Just use what I did previously here, right? So this is the matrix I'm going to have. This is the index of the word. And next, I'm going to, do the dimensionality reduction. So those are just the functions we had previously. Okay. So this is to reduce the matrix over there. So next, first of all, I'm gonna get the matrix norms here. So basically, these 2 steps is how I normalize the matrix over here. Okay. So for this part is also part of the normalization, but it's actually try to extract the matrix norms over there. Okay, so basically it's try to transform the matrix into a square matrix, like a better square matrix with like the same kind of scale between X and Y over there. Okay, I'm not going to go to the details here because this is really mathematical, and I don't think we're going to use that many times. So, but if you are kind of curious about that part, you can just go to this kind of website to find more. Okay. Well, so next, here's where the broadcasting is going to do. So how do I normalize after this? How do I actually do a further normalization of the matrix? What I do here is I'm going to divide all these kind of matrix, all the component side inside this kind of like reduce the matrix over there by the length of the matrix over there. Okay, by the length of the matrix over there. This here is gonna be, if my memory is right, this matrix here is gonna be like n by 1 matrix over there. So basically, it's only gonna give you like a real kind of vector over there. But in order to, but here is n by n, divided by n by 1 by n or n by n. It's not gonna work in in Python here. So what do we do here? Is I'm gonna construct another dimension over there. I'm gonna use NP new axis, NumPy new axis here. Okay, so what does that do? So NP or new axis used to increase the dimensionality of the existing array by 1 more dimension. So basically, it can increase 1D to 2D, 2D to 3D, so on and so forth. For example, if you look at this example, 2018 2018, so that's kind of like 1 row here. Okay, so if you put the new NP new axis as the first dimension, it's going to give you 1 here because previously it's 0. Okay, now it becomes 1 by 4. But if you put this as a second dimensionality position of the second dimension here, it's going to give you 0 to 1. So it's going to be 1 here. So it's going to look like this. Okay, so if you do this again, it's going to give you 4 by 2, 4 by 3, so on and so forth. Okay, so basically here, I just increase the dimensionality by 1 so that I can actually catch up with the dimensionality of reduced matrix over here. So in that way, I can do a normalization. Okay. So after that, you can plot the normalized matrix, just like the function we had previously, right? Here. So we just plot them, and my answer looks like this. Your answer might be a little bit different because we actually set different kind of like random seeds. We didn't actually set random seeds at the beginning, so it can vary across different kind of solution, different people's solution over there. Okay, so this is my kind of answer here. As you can see, we have 1, 2, 3, 4, 4 different clusters. Petrol industry is one cluster, energy, oil, and those bunch of like Middle East countries or second cluster, burial, third cluster, BPD, fourth cluster. Okay. Next, prediction based on word vectors. Okay. So this part is, so this part basically is actually nothing special. It's what we actually saw previously using the GenSim Globe, like a pre-trained vector to do some analogy or contract word comparison. So first, what I do here is from the GenSim downloader, I'm going to actually download the actually not download, actually import the downloading kind of like a function as API here. So after that, I'm going to actually load the Globe Wikipedia kind of like corpus. This is a pre-trained corpus, so this is already like a well-defined like a word embeddings. Okay, so after that, I'm going to print out the length of the vocabulary or this kind of corpus, which is 40,000 here. Okay, at 40,000 for our local drive could be a huge number. So what do we do next when we actually reduce the dimensionality of the word embedding? Is that we only use the 10,000, like a first 10,000, like a last 10,000, like global word vectors, not the entire kind of corpus over there. Okay, so basically what we do is put 10,000, like, did I make it wrong? Yeah, 10,000 globe vector into matrix M here. Then I'm going to reduce the matrix like dimensionality to 200. Reduce the vector from 200 dimension to 2-dimensional here. Okay. So this part is pretty much like what we said previously. See, we didn't put a random seed previously, so that's why the answer could vary between my answer and your answer over there. Okay, but here you can do a random seed, a random shuffle of the word yourself. I don't see anything special here. It's pretty much the same as previously. So basically, construct the matrix is the same. And at the end, you can return the matrix. So basically, it's the same. It's not special. Yeah, one thing I want to mention here is like a try and accept it here. So I recommend you guys, when you actually try to build a new kind of function over there or write some kind of document over there, you can use, I use this like a lot because sometimes when you actually try to test whether the code is working, do some kind of debugging, you don't want to actually look through the entire kind of data set. You just want to try several kind of like a sub data set so that you can see whether it works or not. Actually, so that's where you're going to use the try accept. So basically, you tell Python, I'm going to try this bunch of like code, see whether it's working or not. If it's not working, you're going to tell them what's the next step you're going to do. Okay. So usually what I do here is I try a bunch of like several kind of line of the codes over there. If it's not working, I'm going to actually ask the Python to give me an error message. Okay. Giving me error message here and tells me what kind of like weird. So basically that's going to tell me, oh, one of the 3 lines here doesn't work. Okay. So basically that's it. So after we do everything here, after we do again the matrix dimensionality reduction, the matrix creation, normalization, and we actually got the reduced dimension, reduced kind of like a matrix here. The next we're going to plot it again, use the function we just created previously. After you plot it, it looks a little bit better than the previous cluster, which is very kind of sparse and kind of noisy here. But after this, it's quite compressed. So basically, we have 3 clusters: the petrol, oil, and the country producing the oil is one cluster. Output and barrel to second cluster, and third clusters can be here. Okay, so that's that part. Question 2, 2.2 here. Okay, basically, I wouldn't say it's a question. It's kind of more like exploration. So basically, the it already gives you the function. You just import the function over here. You just import a function over here and then use the function itself. Use a library, import library here, and use a function from here. So what the question is to ask you is find a word with at least 2 different meanings, such as the top 10 most similar word according to the cosine similarity, contain related words from both meaning. Okay, so basically you need to use the most similar function to find a word, and to put the word inside the function is going to give you the 2 different kind of meanings of the similar word to that word. For example, mouse. Mouse here could refer to the mouse we use for the computer, or they could refer to the animal mouse. So I put that inside. It's going to give me a mice keyboard, right? So that's the first meaning. Second meaning, rat. So yeah, so this is a good example. It gives you both meaning. Second, I can use another word, which is a fan here, right? Like a fan could be the fans or the supporters of the celebrities, or it can also be electronic fan, right? So if I put that inside, it's going to give me a crowd, right? Audience, that's the first. And second is going to give me some star, right? That's also the first. But for the fans, it's going to second meaning, electronic fans over there, right? Here, so that's basically that question here, right? Oh, this is actually counterfactual case. Sorry, this is a counterfactual case. This, if you put a fans here, it doesn't give you a second meaning. It only give you one meaning, like fans, crowd, avid, audience, enthusiastic. So that means this kind of corpus or this kind of trained like a vector doesn't really always work. I do have some exception here. Like this could be exception. You can try yourself with other out there. Okay. Second, synonyms and antonyms. Okay, synonyms and antonyms. So what this question asks you is, okay, so basically ask you to actually generate the cosine like distance between different words here. So what I did here is I tried the first word girl, second word woman, last word boy. So if we measure the girl and a woman, like a woman there kind distance, it's gonna give me 0.23. If I measure the girl with a boy, it's gonna be 0.15. Weird, right? Because word girl and boy are like antonyms, not synonyms, right? Those 2 are synonyms. So, oh, sorry. So those kind of 2 words are antonyms, and those 2 synonyms. That's exactly why this kind of number is actually greater than that number, right? So let's try another 2 here. Love, like, and hate. So if you measure the cosines between love and like, it's going to be 0.43. But if you measure the distance between love and hate, it's going to be 4.49. This is a weird part. This is why we do this kind of question. So it means sometimes we do have some exception as well. Why? Because word-to-vec algorithm use a localized window. Okay, because they use a localized window. When we do the word matrix, we actually put a window size over there, right? So inside the window, like the words, like the amount of words is really limited. So it doesn't capture the entire picture over there. So synonyms are not typically used altogether in the same kind of sentence as much as antonyms. For example, if your text corpus is coming from new articles, some of the news articles actually try to do the critical or criticism like comparison between different ideas, right? So within the same kind of window, you could see 2 ideas, yes and no, right? Or right or wrong. Those can 2 kind of words within the same kind of window. If that's going to show up more frequently than the synonyms, so basically that means love and hate shows up more frequently than love and like in the similar kind of like a window size over there. So that's why you're going to have this kind of exception here. Okay. So next part is try to find the matching synonyms. synonyms over there. So basically, what we do here is, I put use the most similar function here and positive and negative. So inside positive, those two words are basically what we're going to match with the man here. For example, if I put a woman and a king here, that basically means man match with king. Then the question we have for the command is what's going to be matched with woman over there. So of course, queen here, okay, and then princess, so on and so forth. So you can do this yourself with different kind of trials. So here, if China match with American, what the Chinese match American? Okay. If London matches with or corresponds to Paris, what does Britain correspond to? France. Okay. So does this have some kind of exception? Yes. So if a teacher corresponds to doctor, what does patient correspond to? Student, right? Student. So it doesn't come at first. It actually comes at a second. That's kind of weird. So next, if old corresponds to grandparents, what does grandchildren correspond to? It should be young, but it only gives you a bunch of like, ages, which is kind of considered to be a teenager, or not teenager, like the young adults over there. Okay. So next is also another bunch of exception over there, right? If man corresponds to worker, what does woman correspond to? Employee, nurse, pregnant, right? So most of like the women are correspond to some kind of like mother or kind of like female characteristics. If we flip it, if we just do women correspond to worker, what does man correspond to? Labor, job, mechanic, so some kind of hardcore work over there. Okay, so this basically tells you like a flip those kind of two words. If we just change the order of the words you're trying to match, it can generate like a greater variation over there. Okay, so again, this is pretty much the same as the previous one, so I'm not gonna reach this part. So yeah, that's basically everything for the assignment one. Any questions so far?
Hey, Daniel, it's Leon here.
Yeah, go ahead.
I just want to add one thing. So when we evaluate like the word embeddings, like say the example that you made, boy, girl, and women. So when we say girl and women are closer to each other, we're looking at their like a gender axis.
Yeah.
But then like girl and boy can also be say they're closer because we look at the age axis, right? So it just depends on like the sub-axis that you're looking at. So because it's like a subspace, so things could be a little bit random, but yeah. Just want to point out.
Yeah, that's a very good point. Yeah, you basically just pointed out that question. So when you actually train the word embeddings, it doesn't capture all these kind of different kind of meanings, right? It only captures occurrence. So what if we just looking at like articles, which is science articles, which just talks about age of the people. In that way, we could have totally different kind of result. But if we only look at social articles, like sociology article that talks about different genders, then this could be the result we have. So this actually depends on what kind of like word embedding you have. And a word embedding depends on what kind of context or what kind of like, the articles or what kind of documents you collect over there. So yeah, I understand what you mean. That's a very good point, yes. For this one, I believe it's based on the gender. I think at the beginning you mentioned somewhere here. Oh, okay, they use Wikipedia. Oh yeah, okay, yeah, so that makes sense. Okay. All right, any other question here about assignment one? All good? No question at all? Okay, now that's about assignment one. If you haven't finished assignment one, keep doing that and make sure you submit it to the Google Drive at the end of a long weekend. If you already finished that, then applause, congratulations. You basically just jump over the first kind of like several chapters pretty smoothly. Okay. So this is how basically we do a lot of like word embedding generations. it's not like a machine learning. It's not like a machine learning. You just need to, put a bunch of like numbers into the models. Sometimes more like the most complicated part about NLP is like you have to generate embedding yourself, because there's no way, the function could generate embedding for you, because you are gonna have really customized or different kind of like a corpus or different kind of dictionaries than anyone else. Okay, so I'm gonna stop here. Basically that's that part. So now I'm gonna jump to the lecture here. So stop share this one here. Sorry, just give me a minute. I'm just gonna connect my iPad to the computer and share my screen over there. Okay. 325. All right, I'm gonna mute myself here. All right, so I'm gonna use my iPad here to show you guys how I'm gonna actually do the lecture. So basically, nope, not that one. Share content, share my screen. Still Zoom, yes. Micro. Oh, yeah. Start broadcast. So, can you guys see my screen here? Yeah, I think you guys can see that. Okay. All right. See what we got. I think we were left over last time here. Okay. Can you guys see this? Because I'm kind of like, sorry, I'm kind of lazy. I don't want to type, the entire lecture into notebook. So I actually just use actually most of the time just actually taking notes, use my iPad here. Okay. So this kind of question actually is part of kind of like related to what we left last time. So last time we actually talked about how do we actually evaluate the word embeddings we just created, right? So there are basically two different kind of evaluations. First one is called intrinsic evaluation. The second one is called extrinsic evaluation. Okay, so you can think about those two. If you are working in an industry like Le Yuan or Xiaolei, you probably heard about this. This is like more like an offline evaluation. This is more like an online evaluation. Okay, so what is intrinsic evaluation? Basically, it's an evaluation of a set of word vectors generated by its embedding techniques over here. But what we're going to do here, we are going to evaluate it on the subtask. Usually this is really naive for some kind of internal task, which is an analogy, kind of compilation, those kind of tasks up there. So this is for the internal purposes, and usually which is treated that are really simple and fast. Okay, so that's why I'm saying this is offline evaluation. Okay, that's offline evaluation. So for example, if you try to do some kind of recommendation engines, then probably you're gonna evaluate it on a bunch of analogy first. Like you put it into the Apple, you just randomly try if I put Apple inside the recommendation engine, what does it gonna help for me? What kind of like a product is gonna generate for me? Okay, so for this evaluation, we actually need to be positively correlated with the final test performance. That is, if this is performing well, that means the final kind of like a task could be actually working. Okay, so several kind of point to summarize the intrinsic evaluation. So it's on the specific intermediate task. So intermediate task means offline, right? It's not like, the final task or production task we're going to have. Another one is it has to be fast to compute, because you try to do some kind of sandbox here. It doesn't have to be perfect. So fast to compute. Next is it helps understand the subsystem, help understand the stop function of the recommendation engine, which is analogy or similarity between the words. It needs positive correlation with the real task over here, right? Because you cannot do counterfactual. It has to be like positive correlated with your final task over there. Okay, so that's the intrinsic evaluation. Extrinsic evaluation basically means online testing or online kind of evaluation over there. So it's on the real task at hand. So basically, it means you have to do that on the real task over here. Okay, it's not on for the internal purposes anymore. And it usually just like, elaborate and slow to compute, because you're doing that on a real task. The data set could be huge, so you could take some kind of time here. So it's an evaluation on a real task. It can be slow to compute, and unclear if it's actually very unclear if the subsystem is the problem or other subsystem. So previously, when we talked about intrinsic evaluation, we actually, what we do is for the subtask. So if you test a subtask, we know whether this subtask is working or not. But for the extrinsic evaluation, you are evaluating on the entire production or entire project. So if the entire project is not working, you don't know which part is not working. Okay, so one is for the sub part, one is for the entire parts. So that's what this means here. So if we replace in the subsystem improves in performance, the performance here, the change is likely good. Okay, so basically, although we don't know which subsystem is not working, if we have a problem with intrinsic evaluation, but if we actually replace or improve one of the subsystem, if it's the entire performance on the extrinsic evaluation is actually improved, that means basically, what we do is probably right. Okay. So that's this part here. Oh, oops. Okay, that's that part here. So any question with the evaluation part? So I don't have a lot of words about this part, because this is more empirical part. It's not like a theoretical part. So it cannot be described with words. Usually you have to feel it yourself when you do a lot of tasks in the industry, or like some Kaggle computation over
there. Question.
Sure, go ahead.
Is this part covered in the lecture notes, like in the videos?
It's not in the slides, but it's actually in the notes.
Interesting.
It's in the second notes over there.
Second notes? Okay.
Yeah, chapter 2, I think so.
Okay, cool, thanks.
Basically, basically this is what academic usually do. What do we do, like when we actually evaluate two different models, like we're gonna do this robustness check using intrinsic and then do the extrinsic here. So that's what Chris Manning just suggested for the industry as well. Okay, so so today we're going to start with chapter 3, word window classification, neural network, and PyTorch. So there are several different kind of parts here. First, we're going to talk about the classification, review and introduction. Okay, we're going to do a little bit like loop back to the classification here. Next is going to be some neural network introduction. Next going to be some enabled entity recognition, like a real task which is correlated with this part. And after that, we're gonna do some kind of like, we're gonna show you the binary, the two different kind of word window classification, binary tree or cropped word, some kind of counterfactual word classification here. And last, it's gonna be some matrix calculus introduction here. Okay, so my plan is actually see whether we can finish these 2 or this 3 part first for today. So I'll do as much as I can here. Okay, so first, classification, review, and introduction. So again, I don't think we should spend a lot of time on this part, right? We all know what classification is. Basically, since it's classification, it means it's a supervised machine learning, right? A supervised machine learning. So basically, you have the label, you have the feature, the input here, but here is what you have is a words, right? Or the documents or the sentences, that could be the input here. And output is a label, is a class, or other kind of words, or other like later some kind of other sentences over there, right? Excuse me. So that's basically the whole data structure for the classification here. So the intuition here is for, I think basically what he wants to talk about is like you already have two types of classification. We can do this way: binary or multi-class, right? We only have the two different kind of those two different kind of like two types of classification here. So no matter which one we are using, we basically just using this softmax or logistic regression classification. Okay, so this is for the binary. This is for the multi-class. That's for the multi-class over there. Okay, so but this one, the logistic regression, is actually a special case of the softmax here. So basically, you can put everything together into softmax. So what we do here is what we try to achieve here is that given the x, we try to predict the possibility of the y. Okay, and we saw this previously before. So basically, you have the input word matrix, you have the input word matrix here as well. Basically, you can just predict every single word you can label by doing this kind of division here. Okay, and this is actually softmax. That's a softmax. Okay. So yeah, I don't think there's too much left to talk about here. So basically, the loss function is this. So previously, we try to max this because we try to max given x, what's the possibility of the y? We try to max that. But since we are doing loss function, so we have to do another way. So we just add a negative sign in front and we do a log to make it easier. Because this is a multiplication. If we do a log, we can have a summation and subtraction. It's a plus minus instead of multiplication or division here. Okay, so this is our loss function for the classification, the classic classification. Of course, you can have a different kind of like loss function over there. Okay, so what's the nature of that? It's actually cross entropy. So the classification function on Earth is a cross entropy. Okay, so what is cross entropy? Cross entropy basically is this. So that's the true possibility distribution BP. That's the true possibility distribution. And the computed or our predicted possibility is Q. So the cross entropy basically measures how similar those two gonna be. Okay, like how close our prediction is gonna be to the real kind of like a label over there. So it's gonna be this formula here. So basically, is a summation of the possibility of each specific class times the log of the possibility of that specific class we just predicted. Okay. But since P here is 0, 0, 1, 0, basically each P is a vector. And inside the P here, excuse me, inside the P here, you only have one here, which tells you this is a label. That's a class you should look for. Okay, since if you multiply that vector with this, you only left with that specific component. So other value is going to be 0. So at the end, of this, because of the one hot like P here, the only term left is actually a negative log like a negative probability of the true class, which is this part. So that means we simplify into this. So Q is actually this. Since P is 1, so is 1 here, right? And we just do here, we just do an average. Okay, so it doesn't matter because when you actually maximize everything, this is not a parameter. So with it or without it, it's going to be the same. So basically, this is the cross entropy. The loss function, softmax, is actually cross entropy. Okay. That's actually the cross entropy here. Okay. Okay. So that's this part. So my question is, what are the disadvantage of this loss function? What kind of disadvantage, the biggest one? What is the critical disadvantage of this loss function? Can you come up with? You can open your mic, we can discuss a little bit here.
What do you mean by disadvantages?
So using this kind of loss function here, the precision or the performance of the model may not be that good as what you expected. What could be the possible reason for the loss function not performing that well?
Is it because the summation on the bottom?
Summation?
I mean, in the softmax.
So yeah, that's kind of close. So I mean, think about this. If you actually, this is the summation, right? Just like what you said, Le Yuan, this is the summation. But what's the weight for each Q here? So this is a Q, right? Think about the summation. What's the weight for each log Q here? It's actually 1 for each log Q. Yeah, it's actually 1 for each log Q here. So for each kind of like observation, for each kind of like a possibility, we just give the weight 1. What if we have imbalanced class? What kind of problem are we gonna have? This gonna be biased toward the major class. Does that make sense to you guys? So it's gonna be biased towards a major class over there. A minority class may not be evaluated enough in the loss function because they all have the same kind of weights over there. Does that make sense to you guys?
I mean, it makes sense, but like usually if you want to give same weight for like have imbalanced classes and you want to evaluate them saying, okay, all classes are equally important, you downsampling the instances, right?
Yeah.
And
yeah.
like say, and also I know you can modify the loss function, but then the problem is like, do you want to minimize the distribution to give the, like to maximize the, do you want to maximize the distribution to fit the curve, right? Like if you have like a majority of classes, you do like intuitively, you do want your model to be like say function like better for those classes. So yeah, it's kind of like tricky, right? Like depends on what your final goal is.
Yeah, I can tell, like, you know, to your point here. So this is the assumption that, you know, I see this is a disadvantage that I value more. I would say this, I value more on the minority. For example, you know, I try to find the pink elephant of all elephant. Okay, if that's your task, if you try to find the minority class, which could be the positive class, which, for example, terrorist detection. You try to capture the terrorist. That means we don't actually value the majority class. We actually value the minority class a little bit more, actually way more than majority class. So if that's your task, then this shouldn't be the function you use. At least you should actually change your weight. Why do we actually use downsampling? Of course, downsampling works, but you're gonna, have some kind of loss of information over there, right? So that's another kind of disadvantage of that part. So it could be the first step. You could try downsampling, but on Earth, if you try to improve like the entire model performance, like you have to start from here because this is the foundation of the entire kind of model. Of course, what you said previously is different case. Like if we care about, for example, for the drug test, Olympic game drug test, right? So both positive and negative class values to us, or kind of like of grade values to us, because you don't want to actually recognize the innocent like athlete into the category of the athletes taking drugs, or you don't want to do the like vice versa. You don't want to do the reverse kind of order as well. Okay, if that's the case, then yeah, it's kind of okay. For the balanced class, and if your goal is just try to predict whether it's in the right class or not, it's okay. But if you only want to focus on the minority, this could not be the best choice you have. Okay.
Yeah, agreed.
That makes sense to you guys? Yeah, basically you have to use weighted cross entropy, yes. Okay. All right, so yeah, that's a little bit of discussion here. So make sure, you always have to do this kind of brainstorm. Don't just take, whatever the lecture gives to you. It doesn't always work in that way, okay? So that's basically that part. So neural network classifiers, okay. Okay, so neural network classifiers. So softmax is actually very, very powerful kind of like, like classification or loss function you could use, because it only gives, it's actually not a very kind of powerful function you're going to use probably most of like time, because it only gives the linear decision boundaries. Okay, only give you a linear decision boundary because no matter what you're going to do here, this is still like, if we do this, so if we just decompose this, a negative log, whatever here, negative log L equals to negative log, A plus log B, right? It's going to be a linear function here. It's going to be a linear function here, and it's going to be a linear function inside here as well. Okay, so it only gives you a linear decision boundaries, but most of the time, like for example, for this one, a linear decision boundary doesn't really help, right? It doesn't really help. So, and even though you try some kind of nonlinear decision boundaries with the classification, for example, some other kind of models like, random forest, right? Or boosting, sometimes their performance doesn't really, isn't that great compared with softmax as well. So in that kind of situation, we actually just switch to neural network. So neural network, you can think about it's a bunch of overlap, nonlinear loss function or activation function over there. Okay. So basically you kind of like stack all the functions together, but they're not linear. You kind of like slowly transform the function so that it touches the boundary of the classification problem right here. Okay. Okay. So the biggest advantage is this part for the classification. So, okay, classification difference with word vectors, artificial neural network. Okay, so the most simple or the basic type of the neural network is called ANN, artificial neural network, which is kind of sequential, which is also sometimes called sequential neural network. Okay, so let's think about the case. Consider a logistic regression classification. Okay. And I'm going to give you guys some kind of notation here. F is a nonlinear activation function. And W, I'm going to explain what the activation function is later. Now just take my words. So F is nonlinear activation function. W is weights. And B is a bias terms. So basically what W is like Y equal to W times X plus B. So this is a weight, that's a bias term. So H is a hidden layer, X is input here. Okay. So what does that logistic regression neural network looks like? Okay. So basically what you do here is first, suppose we only have one layer, one hidden layer. Okay. So you put the input X here into the neural network. Okay. Into a neural network in what way? So step one, X transform into WX plus B equal to Y. Okay. So that's the first step. You're gonna multiply the X, by different kind of like ways here and sum them up to get the next layer. So this is the hidden layer here. Okay. So after that, it's not over. So logistic regression is kind of like start from here. So we start from here as well. So next, I'm actually going to use the activation function. I'm actually going to use the activation function here, okay, to transform the F and transform that into output. So activation function, you can think about it as a transformation of previous layers input into output of the next layer. Okay. So basically, you do a linear kind of summation of all the input data, and we are going to do an activation function transformation, transform this into the output for next layer. Okay. So in that way, what do we do here? For example, this is the F we're going to use, which is a softmax function. That's the not softmax, sigmoid function. Okay. Sigmoid function or logistic regression function here. So that's the activation function we're going to have. So after that, so we're going to have an output over here. Okay. So again, X2 XW plus B equal to Y. Second, Y to FY. Third, FY is going to be the output. Okay. That's the 3 steps over there. Okay. 3 steps over there. Of course, you could have multiple layers over there. For example, if you look at this one, suppose we have X1, X2, X3, so on and so forth. A lot of X over here. And I could have W1 here, 1, 1, W1, 2 here, W1, 2, 3, W1, 3 here. So basically, each X is going to be used for the neurons in the next layer. Okay, and each neuron here basically is a summation of W that neuron. Suppose it's I, or WI, X plus B. Okay, each neuron is going to be look like this. It uses all the X from the previous kind of like a layer over there. But the width here for this neuron is different than the width from this neuron here. Okay, so in that way, we have the first layer, and we can do the same as well, right? We can keep doing that. We can keep doing that right from here, like from this neuron, treat this as a new X1. And we do the same, like we pass that to each neuron here, and each one is going to be, this one here, going to be the summation or the weighted summation of all the neurons here. Okay, and we keep doing that to the next layer, to the next layer. Then at the end, we're going to have an activation function to transform the inputs into outputs. Okay, so that's how the neural network works over there. So why does the neural network going to give us like a nonlinear boundary over there? Okay, think about this way. If think about we start from logistic regression, or think about linear regression. Let's do it this way. This is simple. Linear regression. Okay, and we have the bunch of like X1, X2 until Xn here. So that's the input. Okay, so the first layer could be just W1, X1 plus W2, X2 plus plus B equal to 1 here. Okay, that's a linear regression. Suppose we try to do a linear regression here. So in the first layer, we're going to have Y equal to X W plus B for each neuron over there. Okay, so think about this way. Without the activation function, we're going to pass Y1, Y2, y3 here to the next, suppose this is z1, z2 here. Okay, we're gonna pass that to the next layer. Think about, we do this without any activation function. We don't transform the y, we just pass to the zi. So what z1 is, z1 equal to w yi plus b again. Okay, so if we decompose this, it's gonna be wx plus b. Okay, so still this is linear regression. This is a linear regression. So if you don't add activation function at the end, what you do is a bunch of like nasty linear regression. So what's the difference from the classification problem here? No, there's no difference. You're still gonna get a linear boundary. So the key idea here is like using the activation function, you can like transform this y into a nonlinear z, or z here, and you transform a z into another nonlinear function. So the lot of like curves are going to construct the boundaries over there. So probably in the first layer, you can only construct that part. Second layer, construct that part. Third layer, fourth, fifth. At the end, together, it's going to link together, give you a big like non-linear boundary over there. But if you do a nasty like linear regression, it's always going to give you this. But it's just like, you know, rotating between different angles. By the at the end, it's going to give you a linear boundary over there. Okay, and that's why we actually use the linear. We should use actually, you know, neural network instead of just a simple model previously. That's exactly why what he's talking about here, nonlinear descent boundaries. Okay, any question about this part? Yeah, that's basically the neural network part. So that's a really general introduction to AII. So yeah, as you can see here, right, the first two layer, if we just extract the first two layer, layer 1 here, layer 2 here, A1 would be activation. First of all, you summarize everything, then you do the activation transformation, right? The nonlinear transformation, you get a, you know, A1 here, which uses all the X here, okay? And A2, again, it's gonna be like this, okay? So the next layer, we're gonna do another kind of transformation here, right? So yeah, so that's a summation, a summarize of this, right? So yeah, that's basically how we use the kind of linear, nonlinear transformation between different kind of layers over there, okay? So next part is the name entity recognition here, recognition. So what name entity recognition means is give you, like given a sentence here, for example, we are given this sentence. Our task is actually try to predict the country or location inside the sentence, okay? Or it could be other tasks. For example, given a sentence, let's predict the name of the people inside this kind of like sentence. So that's why we just call it name entity, okay? So it's name entity recognition. It's also one of the hottest, like, you know, kind of like a fields in NLP here. So the task is actually find and classify the names in the text. For example, classify the location, right here. So you have organization, you have location, you have country here, right? So you first find everything here, and you classify all the stuff into the corresponding categories over there, okay? So the possible purpose of this could be tracking dimensions of particular entities, answer the questions, answer the usually named entities, right? And a lot of wanted information, really association between named entities. If you look at this and that, so a lot of locations over there, right? But all the words, it's actually all the words in between those kind of locations, that means a lot. So you can extract a lot of information over there. And the same kind of technique can be extended to other start feeling classifications. So we'll talk about this later. Okay, so that's entity kind of recognition here. So the core idea is actually try to predict an entity by classifying the words in the context and then extract the entity as a word subsequences. But, you know, the name entity recognition could be hard because it's hard to actually cut off the boundaries. For example, given this sentence here, it's really hard to actually classify, for example, the name of the organization. So we can tell First National Bank here, right? But what does that mean? First National Bank is First National Bank, or the First National Bank is the entire organization name, right? Or Future School is a future, like a future version of a school, or is the name of the school here? Okay, so that could be hard. So sometimes, try to classify the organization name or the entity of the name could be hard. For Smith, that, we don't have a lot of disagreement on that part, but for this part, it could be hard. So another kind of challenge could be the recognition of the novel of unknown terms. So what if, you already trained a bunch of like a sentence over there, and suddenly I just give you a new sentence here, or which can give with a name or some kind of terms we haven't used previously in any kind of previous sentences, like Zigala. What is that? I don't even know what that means, right? So what is exactly? Is that a person by the context, or is the more like a location? Sometimes it can be hard, right? So, but actually it's actually the person. So therefore, like an NER could be hard, and it really depends on the context. It depends on which window size you just put over there. So, okay, I guess we'll just stop here, and we'll pick it up. So I actually basically we just stopped here. Okay, so we'll actually pick it up next time between these two parts over here. Okay, so next time we're going to do a little bit more on how to do the name entity recognition using window classification, and how do we actually borrow the matrix to do the window classification. Okay, any question with today's lecture?
I don't have any questions. Just one small suggestion.
Sure, yeah.
I really like the brainstorming part, and when we discuss different ideas, can we have more of those?
Yeah. I agree. I like that as well, because I don't want every one of us just getting the knowledge without thinking about it, right? Sometimes when you actually apply those kind of models into the real kind of case or some kind of projects, we actually need to modify the model. We actually don't use the original version, but how do we modify the model, and what's the purpose of doing that? So you have to think about different kind of perspectives of the model. So yeah, I think I'll keep doing that for more and more kind of when we get more and more kind of models later. But feel free to actually discuss that. So what's the advantage of this? What's the disadvantage of that? Try to think about it that way. And what's the merit of this? What's the shortcoming of this kind of model, right? Try to think about as comprehensively as you can to capture as many details of the model as you can over there.
Yeah, 100%. And I really want to encourage others to speak up a little bit more as well. I feel like that's me.
Yeah, definitely. I don't want Le Yuan to be the only one who is actually open the mic and speak to me all the time. Otherwise, it will be like a VIP meeting between me and him, right? So if you have any comments, just open your mic and talk about it. That's totally fine. Okay. All right. Any other comments, questions, concerns, or suggestions? Okay. So this is my way to present, the my kind of I don't know, the lecture. You can do this, you can do this as well by yourself. But if you are kind of used to the typing or some kind of work online, kind of notebook, you can do that as well. Plus, I think Joyce is you are gonna actually join with me for next lecture delivery. So make sure you contact me through WeChat or add me on WeChat, and talk about what we're gonna do for next lecture. So that's the tradition we're gonna have for the future. So I'm gonna join you guys for each kind of lecture as possible as I can. So make sure you actually add me on WeChat or talk to me 1 week before you're going to deliver a lecture, so that we can discuss what kind of plan we're going to have for that lecture. Okay. All right. All good. Perfect. Okay, thank you guys so much. I'll see you guys next week. Wish you guys have a nice long weekend. Okay. All right, see you later.